this topic, we discuss the accuracy and the precision. When taking scientific measurements, it is important to be both accurate and precise. Under this topic, we will discuss what is the difference between precision and accuracy, rules for combining uncertainties, how to present the final answer in uncertainty calculations. Let's start with the precision. The precision of measurements of a physical quantity refers to how close the measured values are to each other. Let's take this example to understand precision. So here we have some measured values, which represented by black dots, and the true value or the accepted value represented by the white dot. When you consider the first set of measurements, the black dots are close to each other. So we can say the measurements are precise. When we consider the second set of measurements, again, we can say the black dots are close to each other, so the measurements are precise. But in the third set of measurements, we can say the black dots are not close to each other, so they are not precise. Same with the fourth set of measurements. The black dots are not close to each other, so we can say the measurements are not precise. Let's take the same example to understand the accuracy. Accuracy of the measurement of a particular physical quantity refers to whether or not the accepted value of the physical quantity is within the range of the measurements. So our accepted value here is represented by the white dot. As you can see here, the white dot is within the range of the black dots. So we can say the first set of measurements are accurate. In the second set of readings, the white dot is away from the black dots. It is not within the range, so it is not accurate. Same with the third set of readings, not accurate. Fourth set of readings, even though the black dots are not close to each other, the white dot is within the range. So that reading, or the measurements also accurate. Now we consider accuracy and precision together. When we consider the first set of reading, they are accurate and precise. But when we consider the second set of measurements, they are precise but not accurate. Third set of readings, not accurate, not precise. But fourth set of readings, not precise but accurate. All measurements lack certainty. All measurements are uncertain to some extent. Combining uncertainty measurements in calculation produces an even greater uncertainty in the results of the calculation. The number following plus or minus sign, also called the uncertainty or experimental error, that represent the precision of a value. So we use the symbol delta for that. And if we represent G plus or minus delta G, this delta G part or else the number after the plus or minus 0.3 in this case is the uncertainty of the measurement, or else the experimental error, or else we can say the precision of our measurement, which means that the measurement indicates that the acceleration due to gravity lies between 9.6 minus 0.3 and 9.6 plus 0.3. So let's take an example for the precision and accuracy. The accepted value for the acceleration due to gravity in Sydney to three significant figures is 9.8 ms minus 2. Let's take the following measurement obtained by the pendulum experiment. So for G, we got as 9.82 plus or minus 1.65 ms minus 2. Let's see whether this measurement is accurate and precise. If we consider the precision or the experimental error represent the number after the plus or minus sign. So it is 1.65. To see whether the number is accurate, we have to see whether the true value is within this range of the measurement. The range of the measurement we can find out 9.82 plus 1.6 and the 9.82 minus 1.65. So the range is between these two. We can say that the 9.8 ms minus 2, which is our true value, is within the range. So our reading, the measurements are accurate, but they are not precise. Why is that? The spread the measured values are not close to each other. We have 2 times of this 1.65 spread. So we can say the measurements are accurate but not precise. Let's take another example. Here we have again got the value for the gravitational acceleration using the pendulum experiment. It is 9.86 plus or minus 0.03. This 0.03 again represent the error or the precision, and we have to check whether these measurements are accurate and precise. To see whether it's accurate, we find the range. So 9.86 plus 0.03 and 9.86 minus 0.03. So this is the range. So our true value is not within this range. So we can say the measurements are not accurate. However, the measurements are very precise because the spread is only 0.06. If you consider the difference between these two, that is only 0.06. The measurements are not accurate, but precise. Let's see how to combine uncertainties together. So when we have to combine uncertainties together, we divide the calculations to 3 groups. So addition and subtraction, multiplication and division, then the quantities raised to power. Let's start with the addition and the subtraction. If we take 2 numbers, A and B, with the measurement plus and minus the uncertainty, if we want to find the A plus B, we can write this as C, and we can represent C as a measurement plus or minus the delta C. So we should know how to find the C and the delta C. To find the C, this is A plus B, so we can add this measurements together. So that is A plus B. And to find the delta C, we use this equation. So when we are adding or subtracting, the uncertainty will be added together. So we have delta A plus delta B. If we do a subtraction, the rule will be the same. The only difference here is if we want to find A minus B, our C will be different. That will be simple A minus simple B. But our uncertainty will remain the same, and we use this equation to find the uncertainty. Let's take the multiplication and division. If we want to find A times B, we can write that as a measurement plus or minus the delta C. And again here the measurement or else the C will be simple A times B. To find the delta C, we have an equation here. So we use this equation and we find the delta C. So we can find the delta C using the equation. If we have division, the rule will be the same. So A divided by B, we can write as C plus or minus delta C. The C can be found. That should be simple A divided by B. The delta C again will be found using the same equation for multiplication. When we need to find the quantities raised to power, for example, if you want to find AN, again we can write this as a measurement or average value plus or minus a delta C. To find this C, that will be A to the simple A to the power N. To find this delta C, we have an equation again, N times delta A over A. So we can use this equation to find the uncertainty. Here you have some examples. If you are watching this video, you can pause the video and you can do these calculations by yourself to get the confidence of the calculations with uncertainties. Let's see how to present the final answer in uncertainty calculations. Final answer we can represent as the average plus or minus the uncertainty. Now we need to know how to write this average and also how to present this delta C, the uncertainty. We'll start with this uncertainty. The final results uncertainty should be rounded to 1 or 2 significant figures. If the leading digit of the uncertainty is greater than 3, we keep one significant figure, otherwise we keep two significant figures. Leading digit of the uncertainty, that is the first non-zero digit at the left. So this one is a leading digit. This digit is less than 3, so we need to keep 3 significant figures. So we can write this answer as delta L is equals to plus or minus 0.23. We keep 2 significant figures, 1 and 2. Now let's take the second example. Here we have delta L as plus or minus 0.683. In this case, the leading digit is more than 3, so we only keep one significant figure. So our answer is plus or minus 0.7. So we have only one significant figure in this answer. We'll discuss how to present the uncertainty. Now we'll see how to present the measurement or the average value, which is this one. So the rule is the value of the measurement must be expressed in the same form of the uncertainty, same number of decimals in the same units. Let's take these examples. So here we have the measurement and the uncertainty. So uncertainty has 2 decimals, but the measurement has 3 decimals, so that is wrong. To make it right, we need to keep only 2 decimals in the measurement. So if we keep 2 decimals in the measurement, our reading will be like this. So the second one is right. If you consider the third one, you don't have any decimals here, but you have 2 decimals here in the measurement. So to make it right, we multiply both. We keep this 10 to the power 2 common to both the readings. So we make this 12 to 0.12 times 10 to the power 2. Now both are in the same form. Both have 2 decimals in that number. So this is right. For this previous one, we can take this 10 to the power 2 out. So if we take the 10 to the power 2 out, again, we can write it like this. Both have same number of decimal points. So this is right. In the next one, we have centimeters and millimeters. We can't have 2 different units. So this presentation also wrong. Then in the next one, we have both without any decimals, no decimals in the uncertainty and no decimals in the reading. Both the readings are in the same unit, so this is right. So that's how we check whether a reading is presented in the right way. Here again, you have few examples. So you can try these examples by yourself to get confident of doing this. Thank you.